Good day YouTube. Today we'll be having a shot at this year's IMO problem 2. Uh, Really interesting problem. Uh, Before we start, I would like to tell you that this year's problem 2 is a bit easier than the last year's and the IMO 2022 problem 2. So it was not a surprise to see that many contestants got this one right. Um, so let's see what the problem is stating. The problem states that r plus denote the set of positive real numbers. Find all functions f mapping from r plus to r plus such that for each x belongs to r plus there is exactly one y belonging to r plus satisfying this condition. So the key behind having a successful solve in this shot at this problem is to understand this property, that is for each x uh, belonging to R plus there is a unique y which satisfies this relation. Now the thing is, you have to explore this. So how do I translate this into a more usable form? So suppose I fix x naught, then there must be a unique y which satisfies this. So let that be y naught. So the thing is that we don't really get to choose y naught once you have fixed x naught, because of the uniqueness. So let's firstly, to simplify things a bit, let's denote uh, this assertion by f of xy as this one, x of, so this one. So the problem, basically the problem is trying to tell that, suppose so the problem is trying to say that there exists a unique pair x naught y naught such that f of x naught comma y naught is less than 2. So so that means that x naught and y naught, well, it's not just x naught and y naught, we can choose multiple solutions. So for each x, so that means we can choose multiple x's and we will have their corresponding y's. So I'll take advantage of this, and let's take another solution in order to make this more to take good advantage of this property. Let's take another solution, say x1. Before we choose, we'll choose the other unique pair as x1 y1, and in particular we will choose x naught x naught not x naught different than x1, so such that f of x1 comma y1 is less than or equal to 2. So thing is that now uh, the thing is, for x naught there is just exactly one y naught which satisfies this, and for x1 there is just y1. So suppose, just for making the best out of this, let's violate this uniqueness property and say I choose x naught, but instead of choosing y naught I choose y1. Now what would this mean? This would mean that this is not less than or equal to 2, because we have just violated the uniqueness property. So this must be greater than 2. So this implies that f of x naught y1 is greater than f of x1 comma y1. Let's expand it. We have that x naught f of y1 plus y1 f of x naught is greater than x1 f of y1 y1 f of x1. Let's rearrange this a bit. We have that f of y1 x naught minus x1 plus y1 f of x naught minus f of x1, and this is just larger than 0. So now here the thing is that we can conclude that f is actually decreasing. And how do we do that? Well, suppose since we are free to choose x1, like it's not equal to x0, but we are still free to choose. We have the freedom of choosing x1. So let's pick let's make x0 greater than x1. We can do this because x1 is again arbitrary. This would mean that well this part of the we'll notice that this part is negative then if x0 is greater than x1. And not okay, sorry. Let's I'll take another construction. Just excuse me, that was a mistake. So I want this bracket to be negative. So let's see. So I want x0 minus x1 less than 0. So since x1 is arbitrary, let's pick x1 such that x1 is greater than x0. Now we have the now let's see what happens. So now it's obvious to see that this is negative because x1 is greater than x0 and f of y1 is positive. But this means that we must have this bracket to be positive, because if this were negative, then the LHS of this would be negative. If this were negative, the LHS would become negative, and this would clearly be less than 0. So this implies that f of x0 is greater than f of x1. So by this we say f is decreasing. So we have just proved that by taking advantage of this uniqueness, we have you have to make this statement into a usable form. There are multiple ways of doing it, like assuming I have seen other solutions which use y not equal to x. Then if y and y not equal to x for the unique pair satisfying, then x does not y equal to x does not satisfy the assertion. So there are many ways to exploit this, and this is one route. So okay, so now we have f is decreasing. The next thing I'm going to do is I'm going to take the original assertion, and let's now do one thing. Let's take a y. Let's take a y prime, a fixed some real number, such that y prime is greater than x0 and y prime is not equal to y0. Let's see what happens. So this means that f of x0 comma y prime is greater than 2. Well, so this is clearly by the uniqueness property, because x0 y0 is the only pair which satisfies that the original inequality. So this must be true. So this means that Let's expand it out. So we have x naught f of y prime plus y prime f of x naught is greater than 2. Well, but notice f is decreasing, so this means that if y prime is greater than x naught, then f of x naught is greater than f of y prime. So let's this means that this thing, uh, yeah, so this one we can replace it by x naught by putting a bound. So this means that this is less than x naught f of x naught plus y prime f of x naught. So we have that f of x naught plus y prime is greater than x naught f of I prime, and y prime f of x naught is greater than 2. Now since our y prime is arbitrary, so I can make it as close to x naught as I want. What does this mean? I can just approximate it to nearly to x naught. That means that if I take the limit as y prime tends to x naught of f of x naught times x naught plus y prime, this must be equal to 2 times x naught f of x naught. Well, why is that? Because you can see that this part is continuous, because if x naught is fixed, this is a polynomial, f of x naught is a fixed real number, and x naught plus y prime is just a polynomial in y prime for fixed x naught. So this, according to continuity, it must be that limit extends to a is f of a. So that's what I've done. But now this means that 2x naught f of x naught is greater than x naught f of y prime plus y prime f of x naught is greater than 2. Now clearly, if x f of x is less than 1, then x naught f of x naught is also less than 1. But this would mean that 2 is greater than x naught f of y prime plus y prime f of x naught, which is a contradiction. So it must be the case that f of x is at least 1 over x. So this is what we have to work with now. Well, we are almost done now, because if we take f of x greater than 1 over x, then according to the original assertion, which was, so that was what was it, x f of y plus y f of x is less than equal to 2 for all x belongs to R. So this means that, well, we have 2 greater than x f of, so f of y must be at least 1 over y. So this means that this is greater than x over y over x. No, so it isn't. So this means that there is not a strict inequality here, because we have assumed there is not a equality here, because we have assumed that f of x is strictly larger than 1 over x. So assume f of x. So this means, but according to AMGM, this is at least 2. We can't have 2 greater than 2. This is a contradiction. So this means that f of x must be 1 over x. And well, if it's 1 over x, let's see what happens here. So we have that x by y plus y by x is at least 2. Well, according to AMGM, this one is larger than 2. So this means that x by y is y by x is equal to 2. This can only happen when y is equal to x. So this completes the problem that the unique y for each x belonging to R plus is indeed x itself. So that was the and the function satisfying the given original assertion is indeed f of x equal to 1 over x. So that completes the problem. uh, as you can see, it requires the key understanding was this highlighted statement. If you were able to uh, make take advantage and exploit this property as much as you could, then the problem just cracks. So I hope you liked it. It was a fun problem. Thank you. Goodbye.